race do I want to do? That one looks a bit far. So we can Tercero. But I'm in Tercero right now. What about Silo to MU? Yeah, okay. So I'm starting there, and I'm ending up right there in the MU. Okay, cool. Let's go. Alright, oh, I need to turn on my MATLAB sensor. Hold on. Alright, go to the MATLAB app and wait for it to load. That took no time at all. Okay, going over to my sensors, make sure I'm streaming to log, and make sure my position is on, and then I can press start. Great, we're good to go.
Oh, is that another DavisDasher? Good thing I have my position data going. I'm gonna race.
Made it. Were you DavisDashing too?
Yeah, I was.
Boy, that was a tight race.
Should we upload the video and see who won?
Yeah. Time to see who won. Okay, first let's select the right race. Silo to MU. Okay, getting raw data. No will run. All right, it's seeing, it's processing the data right now. All right, and 188 seconds. That ain't bad. Oh, let's see if I can beat you. Okay, getting raw data. John race. 188 seconds. So you took sort of a back route that you went through Wellman. I went down this way, so 154. Haha, gotcha.
Dang. Wow, what a race.
But what fun we had. Hey, I'm John Potter. I'm here with the DavisDash team, and I'm here to talk to you about the beginnings of how we figured out how to plot our data. Simple mesh was the first and most primitive one we came up with, where basically we find the most southwestern and most northeastern points and calculate the slope between those points, just finding a linear equation. And we divide that up into a slope for the x values and a slope for the y value. That has two function components of it: y finder, which you put in latitude, it runs it through the linear equation and outputs the correct y pixel value, and x finder, which is the same thing with longitude. Our second one, array lookup, it creates lookup arrays, which are one-dimensional arrays that have the same length as the number of pixels in the x direction and the number of pixels in the y direction, respectively. So once we have this empty array with certain pixel values filled out with the training data, we can use the linspace function to create data points in between those, because we know the number of data points, because we know the indexes that we need to fill in, and we know the latitude and longitude, which is the actual inputs for the data of these arrays. Once we fill that in with linspace, we can actually use it with the find function. The number of that index is the pixel value at which it should be plotted. Cool.
Hi, I'm Harrison Bolton, and I'm here with DavisDash, and I'm going to show you how the ratio finder approach works. So ratio finder consists of two methods. We have find conversion factors and find pixels. First off, I'll start by showing you through find conversion factors. It takes in your array of latitude and longitude values and a corresponding pixel coordinate on each point on the map. Then it takes the ratio of those pixel coordinates to the latitude and longitude values, takes the average of those ratios, and uses that to be sort of this final ratio that you're scaling each value by in a linear way. So you multiply each latitude and longitude value by your ratio to get sort of a rough scaled approach, rough scaled value. Then you subtract the mean of that set of scaled values in order to get that offset value that you need to make an actual linear transform. Now, this goes into the find pixels method, which takes your latitude and longitude values and finds the corresponding pixel to plot it on the map. Basically, simple linear equation. You take the ratio times the x and y values, then you add the offset, and that gives you a fairly accurate pixel coordinate for a latitude and longitude value. The great thing about these two methods is that as you get more data points, as you get more granularity in your data, you're going to have a much more accurate conversion. So yeah, that is Ratio Finder.
Hey, I'm Rohan, I'm with the DavisDash team, and I'm gonna talk about how we calculated the time it took for the racer to complete the race. So initially we have two starting points denoted by the red circles, and there's the center and a radius around where the person starts and ends the race. Given the calculation of the position, we could determine if they're inside the circle or outside the circle, and with the use of race states, which is in this case, if they're ready, not ready, if they're racing or finished, we could determine whether they're in between races. I use this function right here to tell if they're inside the circle or not, and we could determine that if they're ready for the race and then they immediately go outside of the circle, then they're racing. Given those information, we could determine the time that they start racing, the time that they end their race. We could calculate the time that they took, and with that time, we could go into our overall position data and get the information for the race positions in between time 1 and time 2, which is the racing data.
Hi, my name is Noah. I'm here with DavisDash, and I'm going to be talking about some of the statistics functions that we use for our stretch component. So we wanted to be able to tell our users how far they ran when, or biked, or however they were moving themselves when they were running one of our courses. So to do that, we wrote a function called distance finder that uses the distance formula to find the distance between all of the different pixel points that we can find using one of our functions, ratio finder, which was talked about earlier. Essentially what happens is we take arrays of all the x values and y values, and then we use the difference function to find the difference between all those points. Then we square them and take the square root to give us, in sum, all of those distances, which should give us the distance between the starting point and the ending point, given the path that you ran. We then use the distance that we found with the distance function to calculate the speed and time that you ran the course with. The time is simply t1 minus t0, and the speed is given by the distance over the time. The starting time and ending time are given by functions that Rohan wrote and talked about a little bit earlier, and the speed simply takes the distance from here and divides by the time.
Hi, I'm Harrison, and I'm going to show you how we dynamically upload high score data and pull it from the cloud. So what we're using here is MathWorks' ThingSpeak API, which is basically a free cloud platform that allows us to store up to 8 different variables in individual channels in the cloud and dynamically update them using a MATLAB app. So what we've had done is we take our individual races. We assign each of them a channel, channel 1, channel 2, channel 3, channel 4 for each corresponding race, and then store a matrix of high score values within that. So when you're getting the high score values from the cloud, from this ThingSpeak site, what you get is a string with comma-separated variables. So first, you have to process that, turn that into an array of numbers, and then append, say, a new high score that someone just raced. Once you have that, you just sort the value, push it back in the cloud, easy peasy, and you can just keep your data synced that way. So hopefully this will enable more of a challenge between users where everyone can sort of compete to get higher times against each other. So, fun little feature.